Hello, and welcome to another episode of the book club um, for computer organization and design. We are going into 2.3 here, but before I begin reading, we were talking in the last one, I remember, about comparing the size of, how many lines of code a program would be in assembly versus RISC-V assembly, that is, versus um, C versus Java. And I was, it's kind of, to me, it's kind of a bike shed discussion, like just meant to get people riled up, I think, because, you know, it's obviously going to vary between programs. It's not, they don't give you like an example of, a concrete example. I think it's really meant to just start a discussion, but it's interesting because they suggest in the answer to the check yourself that it's kind of the opposite of what I think. And so I pointed out how even assembly and C aren't necessarily that different. Now, granted, I'm talking about, x86-64, which is different than RISC-V, of course, and you'd expect a lower instruction count. But regardless of that fact, I want to take that comparison just a little bit further, because we looked at the test program from pcalc and compared some disassembly versus the actual source code, but it wasn't really a good comparison because both the original C source code and the test program, or the disassembly of it, had a lot of stuff in it that isn't actually used by the Hello World program. Right? It just pulled all that in because I defined all that stuff because it's actually used in pcalc, which is the actual program I'm writing, right? And the test was just to make sure the syscall worked. That's the only reason that test file was there. But I want to just like do a proper comparison of Hello World, and I don't think that's going to take very long. So let's go to programming, and let's make a directory called like C versus ASM. Okay, now we're going to copy some files over. So we're going to want those files, and we're going to want let's see, we want the test.c as well, right? Okay, so here's some files, and now we're just going to go through quickly and clean these files up. For just what we need. So if we look at Hello World, I think I've been doing some other things in this Hello World, in this test file, but we really only need like this stuff here. Now, I think it's a little unfair that I'm hard coding the length of the string. In reality, you wouldn't bother doing that, and you just call stringlen on it. Now, of course, if you were using a language like D, you could do that at compile time. But in C, you tend not to bother with metaprogramming because it's not built into the language. You would need to write C code that generates C code, right? And have a multi-stage compilation process as a result of that. So generally you don't bother doing stuff at compile time, and you just take the performance hit of doing a little extra work at runtime, unless you're like really optimizing something. So, and that's really just a limitation of the language C, you know, that's just because C is maybe not the best language. So we're gonna use stringlen. We're using the write syscall. And I mean, other than that, you know, we don't really need anything. We can take out that define too, because in practice, you know, well, no, we want the define because we want to have something to refer to get the string length of. No, I think I like this hello world program. You know, I mean, it's not checking the return of write or anything, but you know, we don't really care. So this is what we're going to, you know, compare this program. So the first thing we're going to do is strip out anything from the back end that is not used. So we're not doing any of this stuff. I don't think we need any types. Let's take out all the type defs. Actually, not yet, not yet. Actually, here, let me go back. Is that already the oldest change? Well, yeah, we're gonna want this out of here. We're gonna want this out of here. This, we want the string length. We don't need memset. We don't need memcopy. We don't need break. We don't need connect. We're not gonna have exit because, well, you know, really, maybe we do want exit. In a real program, the thing is we don't technically need it because we're doing an exit in assembly code in the start file. So I'm gonna take it out. This is being generous to see me taking this out, because you could do an exit call explicitly in main. I'm gonna take out the mmap. We don't need read, we don't need socket, we don't need sbreak. We do need write. Okay, now let's take a moment and see what types these use. So we're using an int void size t. We should probably make that int in the actual pcalc, not be using int there, but so we're using s size t, and we don't use null either. So let's say this is our complete backend for hello, super Say in Gunner. I am doing a book club episode, but right now I'm reading, or I mean, rather than reading, computer organization and design. At the moment, I'm just doing a quick comparison between some C code and the equivalent in assembly. So what we have right here, and I think this is everything we're going to want. And then the other thing, we're going to have the start file, and that's going to be shared between the assembly and the C code. Are you a follower from when I do gaming, or are you from, do you watch Risky Business? I don't remember. I'm assuming you're a follower of my Twitch channel. Okay, so... Oh, you just found me, okay. So, I also, just in case if you're not a programmer, by the way, I do gaming as well in the afternoons. So even if you're not into programming, I might still be interesting to watch when I'm playing games. But for now, I'm going to be doing this. So let me find the compilation line here. Can I not copy it like this? Okay, let me do it like this. Oh, nice. If you are interested in learning about the stuff I'm doing, I have on YouTube, if you go to risky.tv, it'll take you to my YouTube channel. And I do a number of different programming series. I do a Risky Business show, which is a long-term project that is right now a lot of studying. And I also do these book club episodes where I read books about programming. So I'm doing computer organization and design. And this is a very introductory kind of text. So I think you wouldn't necessarily need to know much about programming to be able to follow this book. And the other one that I've recently started reading on the show is the RISC-V reader, which is more of a light read, but I've started reading this now as well. So those are all on my YouTube channel if you're interested. All right, so one thing I'm going to do is I also think it wasn't fair to compare with optimizations last time. So we're going to go ahead here and build this. Okay, so here's the assembly that we get. Now, I haven't written enough assembly by hand to know if we were to, like if we want to do a call instruction. If we want to do a call instruction, I don't know if we just do a label if we were actually writing assembly, or if there's more syntax to it than that. So I kind of want to do a comparison where everything is inlined, honestly, although that's not really fair to see. So I think what we're going to do, thank you for the follow. So we're going to take all of this stuff and put it into a file. Okay, now basically what it's going to be is, here, let me go into visual block mode. And we're going to want to get rid of all of this stuff. The actual offsets and machine code, because we don't care about that. Oh, I suspended. Foreground? Is that the... There we go. Well, honestly, I think that is a good way to learn. I do that a lot on my my show for Risky Business, where we read a lot of technical documentation, and a lot of the time it's over my head as well. But I read it anyway, just to kind of, you know, absorb it from osmosis, I guess you could say. And I find that is actually an effective way to start to learn something. So I do think there is something to that, honestly. So I'm just going to write these as labels. And again, I don't know if this is, you know, the valid way you would actually do this in assembly. And we're also missing the data section here. This is only showing us the instructions. But it's going to be a good approximation to how many lines the program would actually be in assembly code. I'm also going to take out start, because that's shared between both the C code and the assembly code. So we're not going to count it. We're just going to count everything else. Okay, so we have basically 58 lines of code for an entire Hello World program. Now, like I say, it doesn't have the actual, you know, the actual string. So, I think it's .db to define something like that in assembly. And I don't know if it's null terminated, but it would be something like this, basically. So this is what I would say is a rough approximation of the number of lines of code you would have to do the equivalent of the C program in assembly. It's like 59 lines of code, okay? That's the takeaway there. Now, if we look at the C program, so do I have, okay. So I just want to know these two files, how many lines of code? So 23 lines of code total for C, whereas it was 59 for assembly. So C does beat out assembly in this case. But again, it's not a huge difference either. It's maybe like around twice as big in assembly. But the interesting thing there too is if we look at the assembly again, we might not be being totally fair to assembly either, because this is taken straight out of the compiler's output. And some of the things it does, like it does no ops to keep things aligned properly. And I don't know if you would actually write code like that by hand in practice. And I don't know if all the assembly it generated is necessarily as good as what you would have written by hand. So that gives you a nice fair comparison, I think, a pretty fair comparison between C and assembly in terms of line count. I just felt that at the last of the end of the last episode that I didn't give that a very fair comparison because we didn't strip the unnecessary stuff out. So now I feel a little bit better that we've done a good comparison there. With that out of the way, we are going to dive into Computer Organization and Design, section 2.3, Operands of the computer hardware. So let's see here. It says, unlike programs in high-level languages, the operands of arithmetic instructions are restricted. They must be from a limited number of special locations built directly in hardware called registers. Registers are primitives used in hardware design that are also visible to the programmer when the computer is completed. So you can think of registers as the bricks of computer construction. The size of a register in the RISC-V architecture is 64 bits. So that's interesting. This isn't the complete sentence, but I think they should mention that that's not always the case. There's 32-bit RISC-V, there's 64-bit RISC-V, and they even, I believe, have things specified so you could do a 128-bit processor. I'm pretty sure they have in the spec things kind of planned ahead for that if people were to want to go that high. But I don't remember that for sure, so don't quote me on that. I know in the D programming language, they have a keyword for it reserved, so I might be thinking of that instead. But for some reason, I'm thinking the RISC-V spec has some like mentions of things being reserved for that as well. But anyway, continuing reading here, they're talking about 64-bit RISC-V apparently. So they say the size of a register in the RISC-V architecture is 64 bits. Groups of 64 bits occur so frequently that they are given the name double word in the RISC-V architecture. Another popular size is a group of 32 bits called a word in the RISC-V architecture. One major difference between the variables of a programming language and registers is the limited number of registers, typically 32 on current computers like RISC-V. This is another thing that I want to take a little sidetrack on now that they're mentioning this. They're talking about the difference between variables that we think of in a programming language and the actual registers that are in hardware. And to me, I've thought about this a little bit, thinking about if you were to build a programming language from the ground up, how would you design it? And one of the very first tempting things you might want to do is use registers directly instead of having the concept of variables at all. And so I just want to walk you guys through a little bit of that design process that goes on when you're thinking about that. So we're just going to call this foo.blah because it's whatever. So we're just going to pretend we're a programming language designer right now, and we're starting from the bottom up. So you know, one of the things that I think it's pretty fair to say, if you're coming from a C-like language, I mean even assembly, you're going to want functions. If you're not a programmer, you might not follow my reasoning here, but let's just start with the assumption that you're going to want the ability to have functions. Rather than writing everything, all of your instructions in one long sequence, you might want to break components up that you're going to reuse. So there's a pattern that you do over and over in your code. So you say, I'm going to make that its separate thing, and then I can just refer to it, right? That's the point of a function. So we're going to want to have the ability to do that in our language. But other than that, let's say we just want to use registers directly. So let's start defining how we're going to do functions, right? So let's just say it's like, you have some type is the return value, and we're going to define it to be like C-style syntax because that's like the thing everybody knows. So we're going to say we have the name of the function, and then we're going to put in, some number of arguments, and I'm just sticking t's in there for now for type, but we're going to, try to arrive at the concept of a type here. So originally these are going to be registers, right? So t's, we're going to call it R rather than T, because R means it's a register. So we're actually taking registers in hardware, and we're going to say like A, B, C, D, and E. So what we're saying is we have A through E are like our variables, but they are actually referring to registers, and we're going to be returning a value through a register. So we're going to do like, return A plus B minus C times D divided by E, and maybe throw in some parentheses there. Just some expression, like we're doing some math, right? So here's a reasonable thing you might want to do in your programming language. Now, the first thing you kind of run into when you're doing this is there are only so many registers, and that's what they were talking about in the book here that they mentioned right away. Is one of the differences between variables and registers is there's only a limited number of registers. So at some point you realize that you're also going to want to pass arguments on the stack if you run out of registers for passing arguments, Or you might also decide, another common thing you're going to want to do in your language is have a struct. So something like this, where, you have some name for your structure, and, you have some members in it, right? And so what you can do with the structure is now you can say like name blah, and then you can say like blah.a equals 42, blah.b equals 1, blah.c equals blah.a plus blah.b. You get the idea. And now when you're using your name function, you're saying, I think I want to pass in as an argument the entire structure. So, I want to pass blah into this thing. Well, how is that going to get passed? Are you going to break the members up and put them in registers? Is the whole structure going to get put on the stack? And what about different types of registers? Here we're talking about registers just abstractly, but they're probably like the general purpose integer registers, right? But then if you want to do floating points, you might have a different set of registers specifically for that. Or maybe we're talking about like SIMD vector registers or something. So you might want to have a few different types for each different type of register. So instead of R, you might have like an I type for the integer registers, an F type for your floating point registers, maybe like a V type for your vector registers, right? But we still have to solve this problem of, how do we deal with the fact that there is, so many different registers, and we're going to want to be putting things in memory too. And it's the thing you realize pretty fast is this is all very tied down specifically to the underlying architecture. The fundamental benefit that you get from using the language C instead of using assembly is that C is abstracted above the point of the actual machine architecture, but it's still low level enough that it corresponds very closely with what the machine is actually doing. So the big benefit that variables give you is if instead of these types that refer to specific registers or classes of registers, if you instead say, we have an int type for integers, well, that's probably, if you define an integer, let's call it foo, right? Foo is probably actually gonna get put in one of those integer registers we just talked about, but it doesn't have to. It can go on the stack as well. It could, be wherever you want. And that's really powerful because this abstraction means it doesn't matter how many registers your machine has. Your machine might only have a couple registers, or it might have hundreds of registers. It doesn't matter, because if your machine only has a few registers, you just compile your code down to use the stack more. And if you have a machine that has hundreds of registers, then you compile it to use all those registers, right? So the code that you write for your program doesn't need to change. And that, I'm not saying that C represents portability in a broad sense, because I think the idea in general of writing portable software is kind of nonsense, and that you always need to have platform layers that are designed for targeting a specific platform. You can never get away from that, as much as people have tried. In my opinion, it's been a failed experiment. if you look at something like even web development, there are so many different configurations of the screen sizes you might have, the DPI, the browser that you're using, what the browser supports, the window size. There are so many different factors, and like, oh, maybe you're on mobile and you want the website to look differently on mobile, but then there's all these different screen sizes on mobile. To actually make a website look good across all these different devices, you know, it's not as trivial as it really sounds. I know Casey Muratori was talking about he was using some like third-party service that you could pay for, I think, to like test your website across like a bunch of different devices and see what it looks like really quickly on a bunch of different devices, so you know you can get it looking good on a wide range of hardware. And so I feel like that's something that is a good idea that you'd want to do if you're designing a professional, like, good website. And then even then, you know, I like to have my font size bigger than normal. And like, look at this. You know, here I just opened up Twitter, right? And look at these buttons. Because my font size is larger than what you would normally use, like the icon and the text are like kind of bleeding into each other slightly. They're slightly overlapping, and the text is like too high. Like, it's formatted badly because the designer of this website didn't factor in the possibility that you're using this particular font size, right? I mean, it's just a disaster when you think about all the different possible configurations. To try to make it always look good is the issue there. And so what I'm saying is that's always a problem. But the thing that C gives you is that, at least in terms of the architecture, in terms of the actual hardware, you're abstracted just above that. So, you know, if you were, you know, talking about like, if your code, you start out saying, you know, you don't even start at this level where we're talking about functions and structs and whatever. You know, let's say you start out, you want to say your language looks like this: EAX plus EDI times ESI or something. Or, you know, you want to say like EAX equals, right? And then, okay, so you're talking about these specific x86 registers. But now what do you do when you want to compile this program on ARM or on RISC-V or whatever else, you know? You can't, because, you know, unless you create something that translates specific registers from one to, like, okay, if you were talking about this register, you should do whatever on the other architecture. You know, that's just a disaster. So it's better to have the abstraction of variables on top of registers rather than talking about registers specifically, because you don't have to refer to the actual registers. So it doesn't matter what architecture you're on. It doesn't matter how many registers you have. It doesn't matter whether you're using a register at all, or if the variable lives on the stack instead. You know, there's a wide range of reasons why you want the abstraction of variables on top of registers. So it becomes very clear very quickly why you would have variables in your language. And so if you just follow this thought process of, you know, we start at the bottom and then we run into, you know, whatever issues, and then we say, well, what's the abstraction on top of that that solves those issues? And that really, I think, is insightful too, if you do that exercise, because it shows you very quickly kind of what C got right. It shows you why it's a good abstraction and what it's really providing you over writing your code in assembly. And to me, the really big benefit of it is portability, not in the broad sense, but in the architecture sense. It really hits the sweet spot in terms of portability. And you really quickly see why the language has structs in it. You see how, the design rationale of how functions work. You see, why you have variables. And that's just from this little exercise of thinking about, do I want to refer to registers directly in my language or not? So, you start with a simple question like that of like, well, the lowest level thing is registers, so maybe we want to talk about that directly. And you quickly learn some very interesting insights just from a mental exercise. So sorry for the large tangent there, but I think that's an interesting thing to point out. Getting back to what they were saying about it, they said how there are a limited number of registers, typically 32 on current computers like RISC-V. And they say see section 2.21 for the history of the number of registers. So that was something we would have read in the previous episode. I don't remember it off the top of my head though, but it's on the YouTube archive. Thus, continuing in our top-down stepwise evolution of the symbolic representation of the RISC-V language, in this section we have added the restriction that the 3 operands of RISC-V arithmetic instructions must each be chosen from one of the 32 64-bit registers. The reason for the limit of 32 registers may be found in the second of our 3 underlying design principles of hardware technology. Design principle 2, smaller is faster. A very large number of registers may increase the clock cycle time simply because it takes electronic signals longer when they must travel further. Oh man, this chapter right here is amazing. It's going over so many interesting things. Here what they're talking about is the fact that the speed of light is a limiting factor in in hardware, because chips run so fast that the actual distance that these signals need to propagate through the circuits can be a limiting factor, because the electrons are only able to move at, or I don't know if they actually move at the speed of light, but it's got to be close to the speed of light, right? They're basically moving at the speed of light, and but because the chip is running on such a tight cycle, the speed of light actually becomes relevant and can be a bottleneck in terms of how fast things can be done, which is why we make our chips so small, why we pack everything together so tightly, because as close as you can get things to each other, the less distance they have to travel, which means, because they're only able to move at the speed of light, the lower the distance, the better, and the faster your chip will be able to run as a result. I don't have a link for you guys off the top of my head, but I want to say it was in the Intro to C series that Casey Muratari did on Handmade-Hero. So if you go to Handmade, now he has his own website for Handmade-Hero, but I don't remember what it is off the top of my head. But if you go to handmade-network, it's obviously a project on handmade-network. Handmade-Hero. So I don't know if the Intro to C is currently on the episode guide. I heard recently it was down because they're getting some Sonera stuff worked out. But so where can we see it on YouTube? Can we just get a link to YouTube? Well, here's the website he has. So let's just click this and it'll take us to YouTube. So handmade-hero, he has the Intro to C series, which was like the first test streams he did when he started up this series. And I know for a fact that he talked about this. He took like the speed of a modern processor, and then he took like a picture of a board and like compared the scale to it with the speed that the processor is running at, and did just like the back of the envelope calculations to show that it actually does matter at that scale and at that speed. Here, let's sort this by oldest first. So I'm guessing it was Intro to C on Windows Day 1, but I don't know that for a fact. I'm not going to keep searching for this too long. Maybe not. But I know he's talked about this. I'd love to be able to find it for you guys quickly. It might have been in a Q&A session too. It might have been why the memory bus is an issue for performance, latency, throughput, and bandwidth. Somewhere in there, I'm guessing, just as a guess. But he doesn't have the links of the annotations in his description. I know Miblo has annotated them, but you'd have to access those through the episode guide, since he doesn't put them in his descriptions. Which, again, I don't know if you can currently get the Intro to C stuff on the episode guide. Like, let's search latency and just see what turns up quickly. So it's looking like this is all handmade-hero, the proper main series. Okay, I'm gonna do one more thing before we give up searching for this. Like I say, it might be in this episode somewhere. You guys can probably find it on your own, but let's search handmade-hero speed of light. I mean, when the page refreshed there, or like when it was switching over, we saw the ruler. So it must have been that episode that we were just looking at. I think that was a thumbnail maybe that it was showing us. So because we saw that, because I saw that, I've got to search through this now.
Here, and what it means, the throughput can actually be quite
okay,
good.
Here it is. This is what he's talking about.
RAM, how fast does light?
So here you can see he's searching the speed of light. Here he's looking up the processor speed. So it's somewhere around here. So it looks like he's on a 3.2 gigahertz processor. This is around 47 minutes and like 40 seconds into the video. Intro to C on Windows Day 3. So if you want to if you want to know more about what I'm talking about, I'm not going to play it here, but look this up if you're curious. It's a great, he just goes through the back of the envelope calculations. He takes the speed of light, he takes a ruler next to a motherboard, and he does the back of the envelope of calculations on why, like, getting from the RAM over to the CPU, why that's a bottleneck. It's like, well, look at the distance and think about the speed of light. It's very eye-opening and insightful, and I think it's a really fun watch. So please look that up if you haven't seen it. I highly recommend it. In that vein, another thing to look up is, like, I know there are posts about, like, memory latencies every programmer should know. And you can see, the scale of different, get a quick reference to the scale of different latencies of, like, L1 cache all the way down to this one's sending packets from California to the Netherlands and then back to California. So a ping to the Netherlands from California. So those types of things are fun to look at as well. And that one's the page is down apparently, but anyway, you guys get the idea. I'll go back to to reading, but yeah, I'm really enjoying this episode today. It's had a lot of good stuff in it already, I'd say. The chapter of the book, I mean, the section we're reading. Okay, so they said that smaller is faster. A very large number of registers may increase the clock cycle time simply because it takes electronic signals longer when they must travel farther. Guidelines such as smaller is faster are not absolutes, however. 31 registers may not be faster than 32. Even so, the truth behind such observations causes computer designers to take them seriously. In this case, the designer must balance the craving of programs for more registers with the designer's desire to keep the clock cycle fast. Another reason for not using more than 32 is the number of bits it would take in the instruction format, as section 2.5 demonstrates. So if you were wondering why it's a power of 2, that's why. It's because it's encoded in the actual instruction format, so a power of 2 naturally makes sense to make the most out of your bits and your encoding. Give me a moment here. I'm just gonna have a little more water. Okay, so chapter 4 shows the central role that registers play in hardware construction. As we shall see in that chapter, effective use of registers is critical to program performance. Although we could simply write instructions using numbers for registers from 0 to 31, the RISC-V convention is X followed by the number of registers, except for a few register names that we will cover later. And then also they had a few descriptions of words they used in the margins here. Double word, another natural unit of access in a computer, usually a group of 64 bits, corresponds to the size of a register in the RISC-V architecture. And word, a natural unit of access in a computer, usually a group of 32 bits. All right, now we have compiling a C assignment using registers. This is an example here. So they say it is the compiler's job to associate program variables with registers. Take, for instance, the assignment statement from our earlier example. F equals G plus H in parentheses minus I plus J in parentheses. The variables F, G, H, I, and J are assigned to the registers X19, X20, X21, X22, and X23 respectively. What is the compiled RISC-V code? All right, so let's open up our Milton here. So let me see. We wrote these out from the last time because they're reusing a previous example. So let's see if we can find where we wrote that out last time. Here we are. So I did add FGH, add GIJ, sub FFG. So now we're just going to replace these with the registers they tell us to use. Now these are probably the registers we were expecting them to use. Let me check the ABI. So they're putting them in starting at X19. So if we look here, where are our registers on our green card? Here we are. Okay, so those are saved registers. So we're putting them in the saved registers. So I guess we're going to just use the registers they told us to use, the X19 through 23. And then I think they're also going to want us to use a temporary register for intermediates. I think, if I remember correctly, this problem needed an intermediate value, and the way we did it, we optimized that away by destroying one of the inputs. Which again, you may or may not be able to do depending on the circumstances, you know, the surrounding context of your problem. But so a temporary register, the first temporary would be X5. So we're going to use X5 as our temporary register and go from there. Okay, so first of all, so let's see, we have F, G, H, I, and J, and they're saying they are 19 through 23 respectively. So that means F is 19, G is 20, and so on and so forth. Just a second. Where did I put my my pen for the tablet? It was under the the lip of the tablet. Okay, so let's rewrite the problem in terms of the registers first of all. So x. Oh, I need to actually. My tablet isn't set up right now, apparently. Okay, just a second. Okay, monoprice 22 Linux kernel module. Alright, and now it just needs to be mapped onto the proper screen. Okay, there we go. So f is going to be x19. So we're going to say x19 equals x20 plus x21 minus x22 plus x23. Okay, now to put these in instructions, we're going to do, so first of all, we're going to do the add of this part right here. So I'm going to say x19 So in x19, we're going to put x20 and 21. So the addition of them. And then we're going to do add. Now this is where I'm destroying G. So instead of doing that, we're going to use x5, the temporary. And we're going to do 22 plus 23. And then finally, we're going to subtract x19. We're going to do x19 minus x5. So that right there, that's my answer. Let's see how they go about doing it. They say the compiled program is very similar to the prior example, except we replace the variables with the register names mentioned above, plus two temporary registers, x5 and x6. Okay, so they use two temporary registers. I just I didn't use a temporary one for the first one because we need to use that register anyway for the result. So why wouldn't you just reuse it? So I feel like it was fine using just one temporary register, but other than that, our answer should be the same. So they use x5 and x6, which correspond to the temporary variables above. they say add x5, x20, x21. So they put, what I did was add x19, x20, x21. So I was skipping a temporary, but they put this in x5 instead, which is their first temporary. And then they say add x6, x22, x23. So again, add x5, x22, x23. I'm using x5 because this is my first temporary, but they're using x6 because it's their second temporary. And then they do sub x19, x5, x6, right? Yeah, they do sub x19, x5, x6. Whereas we already had it in x19, so we just do sub x19, x19, x5. So I would say both answers are equivalent. They're both correct, but mine uses one less register. I only used one temporary register. I don't know if there would be any performance implication there or anything like that. But let's keep reading here. Next up, we have memory operands. Let me see how much we've got left to read. Okay, a fair number of pages left. How are we doing on time? Okay, when did I start this episode? 14:15. Okay, so we've already done an hour. Should we read this next section? I'd like to maybe get through like half of it. So yeah, I'm gonna read the next section on memory operands, and then we're gonna stop there. And we'll finish up 2.3 in the next episode. So, memory operands. Programming languages have simple variables that contain single data elements, as in these examples, but they also have more complex data structures, arrays and structures. These composite data structures can contain many more data elements than there are registers in a computer. How can a computer represent and access such large structures? Recall the 5 components of a computer introduced in Chapter 1 and repeated on page 61. The processor can keep only a small amount of data in registers, but computer memory contains billions of data elements. Hence, data structures, arrays and structures, are kept in memory. As explained above, arithmetic operations occur only on registers in RISC-V instructions. Thus, RISC-V must include instructions that transfer data between memory and registers. Such instructions are called data transfer instructions. To access a word or double word in memory, the instruction must supply the memory address. Memory is just a large, single-dimensional array, with the address acting as the index to that array, starting at 0. For example, in figure 2.2, the address of the third data element is 2, and the value of memory indexed by 2 is 10. So I'll draw out the diagram that they show here in just a second. But before I do that, I'll read the margin definitions of data transfer instruction and address. So data transfer instruction is a command that moves data between memory and registers, and address is a value used to delineate the location of a specific data element within a memory array. Okay, so I'll draw out the diagram we have here. So first of all, we have two rectangles. So we need space for 4 elements. Here, let me put it in grid mode. Okay. Let me see if I can get this to line up better. Oh, this is giving me more lines than I wanted. Get it back to 4 lines. Okay, let's try moving it a little bit. I can't get it back quite perfectly. It's good enough. So here's our 4 sections. Okay, so they drew it upside down of how I'm going to draw it, but it's going to be the same thing. I promise. So between them, we're going to say this keeps going, right? So we keep extending forever going down. Not literally forever, but this is index 0, 1, 2, 3, and so on and so forth. So those are the addresses of the memory, and this, what I've drawn on the screen right here, this is actual, like, representing actual memory in your computer, like actual RAM. And so we're saying, like, this slot right here is, address 0, this one is address 1, this one's address 2, address 3, and so on and so forth. Now, we're gonna put 1 in the 0, 1. We're gonna put 101 here. We're gonna put 10 here. We're gonna put 100 here. And so address, memory. Now over here is your processor. And so they have a line showing that there's communication between them. So this is figure 2.2, memory addresses and contents of memory at those locations. If these elements were double words, these addresses would be incorrect since RISC-V actually uses byte addressing. with each double word representing 8 bytes. Figure 2.3 shows the correct memory addressing for sequential double word addresses. Alright. And so they were saying the value of memory at index 2 is 10. So you see, if you walk through your memory, you walk to address 2, and then you look at the value, well, the value is 10. That's what's stored at address 2. So a pretty basic concept there. It says the data transfer instructions that, the data transfer instruction that copies data from memory to a register is traditionally called load. The format of the load instruction is the name of the operation followed by the register to be loaded, then register and a constant used to access memory. The sum of the constant portion of the instruction and the contents of the second register forms the memory address. The real RISC-V name for this instruction is LD, standing for load double word. Alright, and then we have another example. Compiling an assignment when an operand is in memory. Let's assume that A is an array of 100 double words, and that the compiler has associated the variables G and H with the registers X20 and X21 as before. Let's also assume that the starting address or base address of the array is in X22. Compile this C assignment statement. G equals H plus A indexed by 8. So let me write that out for you guys. It was G equals H plus A indexed by 8. Let's see, did I get that right? G equals H plus A indexed by 8. Yes. So we're saying G is X20 and H is X21. A is an array of 100 double words, and we're compiling this C assignment. All right, so okay, I already forgot what we were saying. G and H is. G is X20, H is X21. So we're gonna have, let me put it over here. I'll rewrite this statement in terms of the registers. So X20 plus, or X20 equals X21 plus A indexed by 8. All right, and then we need to translate this into our final assembly. So I'm going to use a temporary to store the value of A again, because that seems to be the pattern of what they like to do in their examples. Again, you wouldn't really need to use a temporary in this example, but we're going to play the way they want to play, so we'll use a temporary. So for the A, I'm going to put it in X5. So we're going to do a load double word from memory. And let me see the instruction format here for that. So I'm going to reference my green card that was provided with the book. So where is load double? Okay, they don't tell us the format to put it in. They tell us the Verilog description. Of course, I don't know Verilog, so that's Greek to me. But if we look at the Verilog here, it's RRD, so they're saying the destination register equals M RSI plus immediate. Okay. So I think they were saying earlier how all the RISC-V instructions take 3 operands. So it's looking like this is taking, or is that a 1, RS1? It's looking like we're taking a destination register, a source register, and an immediate as an offset. If I'm understanding correctly. Just from trying to understand the Verilog there. So let me just look back on if the book gave us the description of how to structure a load, or if we need to do a bit of guesswork here. Oh, they do give examples. Okay. So let's take a look at LD. Oh no, okay, I'm wrong. It isn't 3 operands. I think it is in the encoding, but the actual assembly code, you do just put 2 operands. But you're referring to a register as well. Okay. I see. So what I'm going to do is I'm going to use x0 as the register to hold the address, because we're starting from 0, and then I'm just going to use 8 as the immediate. So what we're going to do is we're going to say LD x5. Okay, now let me double check the syntax here. Okay, so you put a comma and then you put the offset. So I'm going to say the offset is 8. And then you do parenthesis, and then you put the source register. So you're adding the 8 to the value in the source register. And I'm just going to use 0 for the source register. So x0. And that's the entirety of the instruction. Next, we're going to do g equals h plus x5. So that's going to be add, and we're going to say g is x20, right? So x20, we're adding x21, which is h, and we're adding x5. So x21 plus x5 equals x20 is what this will do. And the x5 was loaded from the previous instruction from memory address 8. Okay, let's compare with what they said. What page? Okay, here we are. although this is a single operation in this assignment statement, one of the operands is in memory, so we must first transfer A8 to a register. The address of this array element is the sum of the base of the array A found in register x22. Oh, I forgot to read that part of it. It says, so let's also assume that the starting address or base address of the array is in x22. Okay, so let's correct our example here now that we're enlightened by this new information. So if we're using x22 as the base address, it's a pretty simple change, I believe. The only difference, I'm pretty sure, would be this is no longer x0. It is instead x22. Okay, let's keep reading. Okay, so they say the address of this array element is the sum of the base of the array A found in register x22 plus the number to select element 8. The data should be placed in a temporary register for use in the next instruction. Based on figure 2.2, the first compiled instruction is LD x9 8 x22. See, now why did they choose x9 this time? x5 was a temporary. Let me double check that. Now, why are they even putting it in x9? According to the ABI, x9 is S1, a saved register. x5 through x7 are temporaries. So even if we're preserving the temporaries from the previous example, you could still use x7. And x9 isn't even for temporaries. So I'm gonna say this is a mistake in the book to use the temporary register x9. Now, in fairness, they haven't introduced us to the ABI in the book yet, so really any register you pick, I think, would be fair game. But I mean, for like the last example, they picked temporary registers that are actually temporary registers in the ABI. So it seems kind of silly now that they picked a register that isn't used for temporaries in the ABI to store a temporary. But anyway, they used LD x9 8 x22. So that's the same thing we did. We just put it in a register that's actually a temporary register. Then they say, we'll be making a slight adjustment to this instruction, but we'll use the simplified version for now. The following instruction kind of operates on the value in x9, which equals A indexed by 8, since it is in a register. The instruction must add h contained in x21 to A indexed by 8 contained in x9, and put the sum in this in the register corresponding to G, which is associated with x20. So add x20, x21, x9. Of course, for us, we're using x5. So we put add x20, x21, x5. Let's see here. The register added to form the address x22 is called the base register. And the constant in a data transfer instruction, 8 in this example, is called the offset. All right, now do we want to continue reading this? I'll leave this, I think, for the next day. Actually, this 2.3 is longer than I thought. We're not even halfway yet. But we're over time already, so I think I'm going to end it there, and we'll continue working through 2.3 on the next episode. So thank you everyone who tuned in today, and thank you everyone who watches on the YouTube archive, which is available at risky.tv. You can follow me at HMN_risky on Twitter to get updates about the series. And thank you also to everyone who supports me on Patreon. It makes the series possible. I'll be providing an alternative to Patreon too for people who no longer want to use the service. But we are still in the process of finalizing what the alternative platform will be. But Patreon will still be using Patreon as well. So if you don't have a problem with Patreon, you can support me on patreon.risky.tv. I will see you in the next episode, and stay risky, everyone.